Section 3.5 Empirical Formulas from Analyses. As we learned in Section 2.6, the empirical formula for a substance tells us the relative number of atoms of each element in the substance. The empirical formula H2o shows that the water contains 2 hydrogen atoms for each oxygen atom. This ratio also applies on the molar level. 1 mole of hydrogen of water contains 2 moles of hydrogen atoms and 1 mole of oxygen atom. Conversely, the ratio of the numbers of moles of all elements in a compound gives the subscripts of the compound's empirical formula. Thus, the mole concept provides a way of calculating empirical formulas. Mercury and chlorine, for example, combine to form a compound that's 73.9% mercury and 26.1% chlorine by mass. Thus, if we had a 100-gram sample of a compound, it would contain 73.9 grams of mercury and 26.1 grams of chlorine. Samples of any sign can be used in problems of this type, but we will generally use 100 grams to simplify the calculation of mass from a percentage. Using atomic weights to get molar masses, we can calculate the number of moles of each element in a sample. 73.9 grams with 200.6 grams per mole, grams cancel, gives you 0.368 moles of mercury. 26.1 grams of chlorine at 35.5 grams of chlorine per mole, grams cancel, multiplied gives you 0.735 moles of chlorine. We then divide the larger number of moles by the smaller number to obtain a ratio of chlorine to mercury. Moles of chlorine to moles of mercury, 0.735 moles of chlorine for every 0.368 mole of mercury. When you reduce that to lowest terms, you get 1.99 moles of chlorine for every mole of mercury. Because of experimental errors, calculated values for mole ratio may not be whole numbers, as in the calculation here. The numbers 1.99 is very close to 2. However, and so we can confidently conclude that the empirical formula for the compound is HgCl2. The empirical formula is correct because the subscripts are the smallest integers that express the ratio of atoms present in the compound. The general procedure for determining empirical formulas is outlined in Figure 313. Figure 313, procedure for calculating an empirical formula from percentage composition. The key step in the calculation of Step 2, determining the number of moles in each element of the compound. If you are given the mass percents of all the elements, how many percentages that each element gives you, assume a 100-gram sample and immediately those numbers turn into grams. You go from grams of the element through the molar mass, go through the periodic table to find moles of each element. Then take the smallest number of moles and divide into all of them and get a ratio. And when you can get a whole number ratio, you've got the empirical formula. Molecular formulas from empirical formulas. We can obtain a molecular formula for any compound from its empirical formula if we know either the molecular weight or the molar mass of a compound. The subscripts in the molecular formula of a substance are always whole number multiples of the subscripts of its empirical formula. This multiple can be found by dividing the molecular weight by the empirical formula's weight. So the whole number multiple, what you're going to multiply the empirical formula by, is found with the weight of the molecule divided by the empirical formula weight. In sample exercise 313, for example, the empirical formula weight of ascorbic acid was determined to be C3H4O3. This means the empirical weight is 3 times 12 plus 4 times 1 plus 3 times 16 equals 88 AMUs. The experimentally determined molecular weight is 176 AMUs. Thus, we find that the whole number multiple that converts the empirical formula to the molecular formula by dividing the molecular weight of 176 by the empirical weight of what we found. It was 88 and end up with 2. Consequently, we multiply the subscripts and the empirical formula by this multiple. You multiply every atom in the formula by that multiple. So C3H4O3 becomes times 2 is C6H8O6. That's the molecular formula. Combustion analysis. One technique for determining empirical formulas in the laboratory is combustion analysis, commonly used in compounds containing principally carbon and hydrogen. When a compound containing carbon and hydrogen is completely combusted in an apparatus shown such as in 314, the carbon is converted to carbon dioxide and the hydrogen is converted to water. The amounts of carbon dioxide and water produced are determined by measuring the mass increase in the carbon and the water absorbers. From the masses of the carbon dioxide and water, we can calculate the number of moles of carbon and hydrogen in the original sample and therefore the empirical formula. If a third element is present in the compound, its mass can be determined by subtracting the measured mass of carbon and hydrogen from the original sample mass.